But anyway, just saying that to make sure you know that I'd be happy to answer questions about it if there are questions.
I actually was wondering, I have a question.
Sure.
I was wondering if my program prints out a correct solution, does that mean that it works for all of the solutions? Since we're not basically doing like an exhaustive um, algorithm on it to print out all possible solutions.
Um, I, sorry, I'm a little distracted here. Are you guys getting any kind of echo or anything at all?
No, it works.
No, I'm
okay,
fine.
good. I just realized that I usually have headphones on when I do this and I don't have them on. But as long as it's working, I guess we'll go with that. All right, so question was, if your solution finds the one solution or finds a solution, does that mean that it's correct or that it would find all the other solutions? Is that a good characterization of your question?
Yeah, exactly.
Yeah. That's a good question. I mean, it would be really hard to imagine that would not be the case. I suppose that it's possible. I don't think that we're, in order to make sure of that, you would have to do a lot of work, right? You probably have to do the amount of work you did already times 10 and come up with a solution that generates all possible answers and check that. But I think it's probably not worth doing 10 times the work at this point in this course to make sure that you actually have a solution that's going to work all the time.
Right, I'm not talking necessarily about this problem, just in general, I was thinking about it, how would you even test, if you can get multiple correct solutions? Or all of the solutions you would get are correct. Since the program that I have prints the same solution every time, basically.
Right, and it should. So yeah, I think like Kaylin said, your question is like a major issue, right? I mean, how do you know that just because your program worked the first 10,000 times you tested it, it's going to work the 10,001st time? So I guess the short answer is there's no easy answer to that, and you do the best you can to test everything. I don't know if that's an unsatisfying answer or not, but I think it's reality.
Okay,
yeah.
Thank you.
And there's an area of study in computer science where called validation, where you actually try to use formal proofs to prove that your algorithm works. But that is, successful to a limited degree.
That's good to know.
Okay. Anyway, so let's talk about chapter 6 a little bit. Well, we're going to be studying a new abstract data type. Tell me what abstract data types we have studied in this class so far.
Bag.
Bag. It's only one more, I think.
Linked list.
Good answer. To be really technical, we didn't actually study a linked list abstract data type. We studied a linked list implementation of another abstract data type. Does that make sense? It's actually, maybe it's a little technical, but it's also an important distinction, right? Because one of the most important things we need to understand from this class is keeping straight between implementation and the client, right? So The other abstract data type that we've studied besides bag is set, right? We wrote our own sets. And that's basically the only abstract data types we've done so far. So basically what we're going to be starting today is we're going to just start going through a bunch of other abstract data types. And for each one, we're going to talk about how to use it, and we're going to talk about how to implement it. And in this text, one of the things I like about this text is that for most of those cases, he actually has that split into two separate chapters, right? So there's a chapter on stacks, and then there's a chapter on, okay, how do we implement a stack? And so you can implement a stack, for example, using an array, or you can implement a stack using a linked list, or, you know, there's other ways you could potentially implement a stack. Anyway, so short answer to my question is we've studied bags, we've studied sets. That's two ADTs. Did I record? Yes, I did. Okay. So today we're going to study stacks. That's the next ADT, and it's the next simplest ADT, in some ways even simpler than bags and sets. Let me start with a picture from the text that I think is pretty cool. All right, you guys see in the textbook now?
Yep.
All right, so does this picture look familiar to anyone at all?
That's a stack.
That's a stack, right? It says here that it's a stack of cafeteria plates. Has anybody ever seen a stack of cafeteria plates like that? I'm not sure if that's still, those things are still around, or if that's kind of showing my age. But anyway, when I was a college student, this is what our cafeteria stacks of plates looked like. They were in these carts, but they were sunk down, so you could only see the top plate. And so you took the top plate out of the stack. And so that's really the best analogy that I think there is to what we are talking about when we talk about a stack data structure, right? You can only put things at the top of the stack. You know, if I have a plate, I can't go in and put it down here in the middle somewhere. I can only put it at the top. I can only take its plate off the top of the stack. There's no way to take off like the top 4 plates. You can't do that. You can only get to the top plate. So that's a stack. There's other analogies for a stack, right? You could talk about, you know, just a stack of books sitting on the table or something. But I kind of like this analogy better because of how it is obvious, how it prevents you from getting, I mean, a stack of books, you could say, oh, come on, I could take the top 4 off and reach the 5th one, right? That's not the way a stack works. Excuse me while I move my windows around a little bit here. Okay, right, so it is, the way this works is that the last plate I put in is going to be the first one I take out, right? So that's where we get the term LIFO or LIFO, last in, first out. Okay, so let's look at some, what an actual abstract data type for a stack might look like. Here are the operations that we're going to have for stacks. We're going to have a function that tells us whether the stack is empty or not. We're going to have a function to push a new entry onto the stack. We're going to have a function to remove an element from the stack. And we're going to have a function to look at what the top element in the stack is. Okay? This is a little weird. Most of the time, you're going to see this function named top, not peak. In fact, I can't remember for sure, but I think he may change that in the 7th edition of the textbook. Anyway, and that's basically it. There, if you first in, last out, that would be correct, John. Not, for whatever reason, that's not what most people have come up with to call it, but that would actually be technically correct. Let's, just for fun, look at c++.com. And I will share that in just a second. Just to save you the trouble of having to remind you. So if we look at c++.com and we want to find out about the STL stack, here we go, stack. And you'll find out that here are the member functions, okay? There's empty, which corresponds to the is empty from the text. We're gonna, there's also a size member function. There's top, which the text calls peak. And then there's push and pop. And then there's these other things called in place and swap, which we're not gonna talk about. They're useful, but they're not really part of this sort of classical definition of a stack. So we're gonna kind of skip over those. Okay, so basically exactly the same member functions that you saw from the textbook, plus a size function, and instead of peak, we call it top. Okay. Oops. Okay, so here is the actual C++ code for our stack interface class. You'll note this is pretty similar to like the bag interface class or the set interface class. It's simpler though, right? Only 4 member functions. With size, there would be 5 instead of, I don't know, in the bag class, there were probably like what, 8 or 9 or 7, something like that. Anyway, there you have it. We will eventually, this week, yeah, actually part of the assignment for this week will have to do with implementing a stack, and this will be the interface file that you will be using for that. All right, just to play around a little bit, let's look at these questions. I don't want anyone to actually answer this yet. I just want you to kind of ponder this for a minute and see what your answer would, think about what your answer would be. If you push the letters A, B, C, D in that order, onto a stack of characters and then pop them, what order will they be deleted from the stack? Someone want to raise your hand and tell me what the answer to that question is? And raise your hand and then I will call on you and you can tell me what the answer to that question is. Go ahead, Mark. You can either type in the chat or you can...
reverse order, right?
That
so
is,
like DCBA?
DCBA, right. So you would push the A on the stack and then push the B on the stack and push the C on the stack and then push the D on the stack. And then when you start popping, the top thing on the stack is going to be the D, the last thing you put on, right? And you pop the D off and then the next thing on the stack is going to be the C. For the upcoming assignment, the textbook actually has a function. The textbook actually has a working stack class, and I'm just going to have you modify it. more or less. I'm going to have you modify a modified version of it. Okay, let's do, I'm not sure if that, if everyone got that or not. If you want me to talk about that in more detail, please just say something or type something in the chat. But in the meantime, why don't you guys, I'm going to give you guys, I don't know, 60 seconds or so. And I want you to tell me what the answer is to question 2. Once you've got an answer, go ahead and raise your hand. And I'm going to wait until, most of you have your hands up before we go on, okay? Just to make sure everyone's tracking with this. Go ahead and keep your hands up. I'm kind of waiting until the majority of you have your hands up, so I know that I've given you plenty of time to think this through. I just, while there was silence there for a minute, I actually worked it out on a piece of paper myself, so I know the answer. Okay, so maybe I would be mean here and actually call on somebody. Oh, as soon as I said that, 2 people put their hands down. Hands don't go down automatically, right? If you put your hand down, that means you...
Oh, right. I just figured you had reached the threshold for people.
Okay. Let's see. Okay, go ahead and put your hands down now. And then leave it up if you're willing to tell me what your answer is. Sorry, that was confusing, huh? Oh, come on, more people than that. I've got to be willing to give it a shot. Patricia, you want to go ahead and tell us what you got for the answer to question 2? You can either speak it or type it in the chat or...
Was the question, what do the stacks actually contain?
What do they look like after the following sequence of operations? Yeah, so I think that's just another...
Okay, so stack 1 for me, I start the top to bottom is 5, 4, 1.
Okay.
And stack 2 is 6, 3.
Okay, that's what I got too. Anybody raise your hand if that's the same answer you got. I'm going to make you guys get really good at this hand raising thing. Helps me a lot.
You do mean the raise button hand, or that raise hand button, not like physically raising our hands, right?
Guess I should be clear about that, huh? Given that only 2 of you have your video on, I think it would probably work a lot better this way. Okay, so I guess I'm kind of thinking that we should go through this So I just want to make sure everyone's tracking with this. Let me. So. This is driving me crazy. Okay. I'm going to share my whole screen now. Okay, so you guys are able to see the question and also the Word document now. Is that correct? Oops. That's not what I wanted. Jeez. No one answered me. You guys are looking at an empty Word document in the text.
Yeah, we can see it.
Appreciate that. Okay, so I'm just going to draw a picture of the stacks left to right, which I hope that isn't too confusing, but it's fairly common because it's just easy to type that way. So the top of the stack is going to be going out to the right. So stack 1.push1, stack 1.push2, stack 2.push3. Stop me if I lose anybody, okay? Just type something in the chat window and say, wait. Stack 2.push4. Stack 1.pop means take the top element off of stack 1. Stack top gets stack 2.peak. So I guess I could actually type that. Stack top is equal to 4, right? Now stack 1.push stack top, so that means I'm getting a 4 right here. And then stack 1.push5, get a 5 on the top. Stack 2.pop, that means remove the top element from stack 2. And then stack 2.push6. Okay? Any questions about that? Okay, let's talk about how we might use a stack. First question I want to ask is, how might we, just think about this for a second, how might we use a stack to test a string to see whether that string has balanced curly braces or not? Anybody want to raise their hand and talk about that a little bit when I call on you? How would we use a stack to test a string? So imagine we have a function, and the function takes a string as a parameter, and its job is to look at that string and return true if the curly braces in that string are balanced. In other words, I guess I'm hoping you know what I mean when I say balanced curly braces, right? Like as if it was an expression. John, you want to go ahead and take a shot at that?
Yeah, 2 stacks, and for each open brace you get, you would just want an equal number of closed braces. So 2 separate stacks, add to 1 every time you encounter an open brace, add to 2 every time you encounter a closed brace. At the end, compare the amount of braces.
Okay, interestingly, that would work in this case. It doesn't really take advantage of the stacks though, right? Because you could do the same thing with, I don't know, like Actually, you could do exactly that same thing with just counters, right? You could count how many open
Definitely.
braces there are, and you could count how many closed curly braces there are. And as a matter of fact, I think that wouldn't quite work, right? Because you could have a closed brace before an open brace, and that algorithm would still return true.
Yeah.
Makes sense? Okay. Thank you for taking a shot at it. As I think I've mentioned before, wrong answers are often the best ones. So let me actually go ahead and try to explain how this would work. Well, actually, you know what, Kaylin, you want to take a shot at it?
I think I got it. So what you do is anytime you find an open brace, you go ahead and put it on the stack. Anytime you find a closed brace, you go ahead and pop something off the stack. If the stack's ever empty when you find a closed brace, you're in trouble. And similarly, if you get to the end and the stack isn't empty, you're in trouble.
Correct. How does that sound? Does that make sense to everyone? Anyone want me to say that again? Maybe slightly.
Makes sense.
So one stack, every time you see an open curly brace, push it on the stack. Every time you see a closed curly brace, if the stack isn't empty, then you pop an open curly brace off the stack. If the stack is empty when you see a closed curly brace, that means that you have too many closed curly braces and you'll return false, right? Then when you exit this loop, if it turns out that there's still stuff left on the stack, that means you had too many open curly braces, and so you return false. Okay, so that's super, super simple. You can imagine that you could extend this out to actually evaluating actual arithmetic expressions with parentheses and square brackets and curly braces and whatever. So this is like the super, super simplified version. But let's go ahead and take a look at the code for that, or pseudocode anyway. That's going to be right here. And this is basically what Kaylin and I were just talking about, right? Would it help if I made this bigger? Anybody want me to make this bigger?
It's fine.
All right. So basically, we're saying I is going to be the counter that's counting through the string. And he has this interesting philosophy of not wanting to return a value from inside a loop. So that's why he's got this balanced so far variable. So basically, as long as things look okay so far and I haven't reached the end of the string, I'm going to say if the character at position I is an open curly brace, push it on the stack, just like we said. If it's a closed curly brace, if the stack isn't empty, pop it. If the stack is empty, then balance so far gets false, which means we're going to exit the loop and return false. Okay, so then we go all the way through the string. If we get all the way to the end of the string and we come down here, if the stack is empty, we return true. Stack has balanced braces. If the stack is not empty, then we return false. Okay. Anybody want to ask a question about that? Okay. So I thought we would just take a minute and go through question 3. I don't know. I'm trying to decide whether that's too much. No, let's just do it one. Let's do one real quick. So I'm going to do this with columns. We're going to do question 3A. So the input is going to be X, open curly brace, Y, T, close curly brace. brace, close curly brace, close curly brace. And then going back up to our algorithm, I think this might actually be, I can't remember. No, I don't. I was going to say you might have to do this in your homework, but I think I was wrong about that. So let's trace through this algorithm using this as the input. Okay, so I, ch, stack, at, and so we all want to draw a picture of what the stack looks like at the end of each loop. Okay, so to start with, I is 0. The character at position 0 is x. And what we do is nothing, right? We ignore any character other than an open curly brace or a closed curly brace. So the stack at the end of the first iteration of the loop is going to be empty. I is 1. The character is an open curly brace. And so what we do, let me think about that for a second. Actually, it's not actually shorter because in terms of, by shorter, you mean fewer iterations through the loop. I don't think that's true because he's going to stop the loop with this. Fewer lines of code. Yeah. Yeah, you're probably right. Yes. No disagreement there. Okay. 1, open curly brace. And so in this case, in the case of an open curly brace, we push it on the stack. Okay, next time through the loop, I is 2. CH is open curly brace, and so we push it on the stack. Okay, next time through the loop, I is 3. Character is Y. So we do nothing. Stack stays the same. I is 4. The character is Z. So we do nothing, and the stack remains the same. Next time through the loop, I is 5. We see a closed curly brace here in the string. So what we do is, because the stack is not empty, what we're going to do is pop the stack. So at the end of this time through the loop, the stack is going to have a single open curly brace. Next time through the loop, I is going to be 6. Closed curly brace is the character in the string. If character is a closed curly brace and the stack is not empty, what we do is we pop the stack, and now the stack is empty again. Come back up to the top. I is 7, and the character at position 7 in the string is closed curly brace. And so we look at our code here. If CH is a closed curly brace, if the stack isn't empty, well, the stack is empty, so we do the else part, which means we set balanced so far to false. What's going to happen is that's going to cause us to exit the loop and return false. All right. Any questions about that? We could have some fun, and we could do an example where it actually matches. We could do an example where there are too many open curly braces, but I think you get the point. And we will have more chances to trace through stuff. If I remember correctly, that your homework, the written part of your homework for this week basically consists of doing this sort of thing where we're tracing through an algorithm. Okay, next example. We're going to use a stack to write some pseudocode that determines whether a string is in this language. Okay, so look at that. We're actually using the stuff we learned in the last chapter about languages and grammars. So in this case, we have S $, and then S prime, where S prime is the reverse of S. So here are some example strings that are in the language. Basically what this is a palindrome, but there's an additional requirement that there's a $sign in the middle, right? So what we're going to do is we're going to use a stack, and this is very similar to the matching curly braces idea, right? A little more complex though, because we need to make sure that we have the right correct character there. So every time we see a character, we're going to push it on the stack until we get to a $sign, at which point we're going to start popping things off the stack and making sure that they match the next thing in the input in the string. That makes sense? And we want me to say that again? Or better yet, we can actually look at the pseudocode. That's quite a bit more complicated than just matching the curly braces, right? But just to kind of look at the idea here, we're going to, as long as the CH is not a $sign, we're just going to push characters onto the stack. That's what this loop here does. Now we can come in I to skip over the $sign. And then at this point, what we are doing is we're going to take a look at the top of the stack and also pop the top element off the stack. And then we're going to say if the item at the top of the stack that we just popped equals the next character in the input string, then the characters match and we're good. So we're just going to I++. Otherwise, we fail, right? And so if we wanted to, we could actually just say return false right here. Then this else is if we got to this point and the stack was empty, in which case that means we got too many characters on the right side of the $sign, so we would say in language equals false, right? Okay, and then when we finish all of this, if the stack is empty, we're in good shape. If there's still stuff on the stack, that means we had too many items on the left side of the $sign, and so we would return false. Any questions about the pseudocode? Someone said yes, but I'm guessing that was from a while ago and I was asking something different. Cool. All right, so not surprisingly, the next thing we're going to do is we're going to trace the execution of that language recognition algorithm. And hold on a second. So I think I may, you have to do a question like this in your homework. So, all right, let's just do one. Let's do part C. So this is question 4C. The input is going to be A, B, $sign. A, B, $sign. Okay, so you're going to do a similar thing with the columns. We need I, we need CH, and we need stack. A little more descriptive than just saying stack. So I starts at 0. When I is 0, the character in the string is the A. And so we push the A onto the stack and we increment I. So next time through the loop, so for I and CH, I'm typing what the value of those are at the start of the loop. And then for the stack, I'm saying what the value is at the end of the loop. I think that makes more sense. So the character at position 1 is B. And so what we're going to do is we're going to push that onto the stack so we get AB on the stack. Next time through the loop, I is 2. Character at position 2 is $. And so since CH is not a dollar, since CH is a $, we exit the while loop and we don't change anything to the stack. Okay, so now we increment I again. So now we're down here at this while loop. The character, let's see, while the stack is not empty, stack top equals stack dot feet. So I'm just going to remember that that is B, right? Stack top is going to be B. CH is the character at position I in the string, so that's going to be A. So if stack top equals CH, it does not, right? So we're going to do the else, and we're going to say in language, it's false. Which is going to cause us to exit the while loop and return false from the function. Okay? That was a pretty super simple example, but I don't think it would be too hard for you to expand that into an expression that's slightly a little bit longer. Any questions about that? Okay, now we're going to get into the actual real stuff. Using stacks to evaluate algebraic expressions. This is exactly what I'm going to have you do as part of your assignment this week. You're going to write a function that evaluates expressions. And you're going to do that in 2 steps because evaluating an infix expression directly is really difficult. So what we're going to do is we are going to first convert the infix expression into a postfix expression. It turns out that that's the hard part. Then the easy part is going to be evaluating that resulting postfix expression. So let's first talk about how to evaluate a postfix expression. Basically what you're going to do is, here's the pseudocode. For each character in the string, if it's an operand, push the value of the operand onto the stack. If it's an operator, you're going to let operand 2 be the top of the stack. So if you see an operator, that means that there's going to be 2 operands sitting at the top of the stack. That's just the way postfix expressions work along with this algorithm is that anytime you see an operator, you know there's going to be 2 operands sitting on the stack. So pop the stack and assign that to operand 2, pop the stack again and assign that result to operand 1, apply the operation to those 2 operands, and then push the result back onto the stack. That's all there is to it. Okay? So Let's trace through that code using an actual postfix expression. I'm going to use okay, there's my postfix expression. So let's evaluate this. Let's trace through this pseudocode here. I'm going to have a column for CH. I'm going to have a column for op1. I'm going to have a column for op2. I'm going to have a column for what the stack at the end of the loop. All right, so CH is A the first time. And all we do is, since it's an operand, is we push it onto the stack. So there's no op1 and there's no op2. We just push A onto the stack. Next character is a B. Push it onto the stack. No op1, no op2. Third character is C. Same thing. Every time we see an operand, there's no op1, there's no op2. We just push it onto the stack. Okay, next character in the string is a minus sign. That is an operator, so we're going to do the else part. We're going to let op1, op2 is going to be the top of the stack, which is C. And then we're going to pop the stack again and assign that to op1, so that's going to be B. And we just popped two things off the stack, right? So now the stack is going to be just A, right? I forgot to tell you one important thing. These numbers, these letters, operands are actually going to have values. So A is going to be 7, B is going to be 3, C is going to be 12, D is going to be -5. Okay? So now there's a lot going on here in this step, right? I just popped two things off the stack. That's why when I type this over here, it just has an A and not a BC. But then the next thing we do before we finish up this iteration of the loop is we push result onto the stack. Result is operand 1 minus, in this case, operand 2, or to be more specific, B minus, B is 3, so 3 minus 12. Result is 3 minus 12. So now what I have on the stack is I have A minus. It might actually make more sense for me to actually put the numbers in here. That's a little confusing, but we're going to go with this one now. Okay. Next time through the loop. Isn't op1C. Okay, well, look what we did. We said the first thing we did, so let's go back to this point here. We just finished this iteration through the loop. Now we go back up. Oh, okay. So let me just go through that again anyway, just to be super clear. So when we got to this row here of the table, the character was minus. We get to operand 2 gets top of stack, and the top of the stack at this point is the C. So operand 2 gets the C. And then the next thing we do is operand 1 gets top of stack. At that point, the top of the stack is the B. So operand 1 gets B, and then result gets 3 minus 12. Okay? and then push that -9 onto the stack. Next time through the loop, the character is D, and because that is an operand, we just push it onto the stack. So A -9 D. Okay, next time through the loop, the character is star. So we say operand 2 gets top of stack. So operand 2 gets the D, which I'm just going to type it. The D is -5. Operand 1 gets what is now at the top of the stack, which is the -9. Okay, and then result gets operand 1 times operand 2, so the result gets 45. And I push 45 onto the stack. So now the stack is going to look like this. All right, we popped off the D, we popped off the -9, and then we're pushing the result, which is a 45. Okay. Last time through the loop, the character is plus. So we are going to do the else part. Operand 2 gets top of stack, which is A, which is 7. Oh, no, I'm sorry. Operand 2 gets top of stack, which is 45. Operand 1 gets top of stack, which is the A, which is 7. We just popped the A and the 45 off the stack. Now we're going to say result gets 7 plus 45, which is 52. And then push result onto the stack. So we push 52 onto the stack. And so now we're done with this algorithm. And when we're done with the algorithm, the result is that the value of the expression is sitting as the only thing on the stack. Okay? All right, so that's it for today. On Thursday, what we're going to do is we're going to go over the pseudocode for converting an infix expression into a postfix notation. We're going to go over the pseudocode for converting an infix expression into a postfix expression. And then we're going to move on to chapter 7 and start talking about how to implement stacks. Any last minute questions before we go? All right. Okay. I'm going to cut out so I can go to my next meeting, and I will see you.
Thank
Thanks
you.
for class.
All right.